All right, if you're ready, I'm ready. Problem number 1. 6-1. Ooh, this pen is a little bit too thick for that. Problem 6-1. A roller coaster. You are on a roller coaster at location A. You're a daredevil. And you go down here from point A. Here you are in your roller coaster. You're sitting there innocently, at least at this moment in time, not being aware of the terrible things that are going to happen to you. You start with speed 0, and there you go, yeah, and you go inside this loop upside down. Let us call arbitrarily the gravitational potential energy at the ground level 0, so U equals 0, and let this height of A above the ground level be h. The radius of this circle, let that be r, and this is point C, and let this be point B, the highest point of the circle. And this separation here, the distance of point B above the ground, would be 2r. Now, let's assume there is no friction, so mechanical energy is completely conserved. You have no kinetic energy here, you have only potential energy, and you pick up speed, and you reach point C with a velocity which I call v of c. You're climbing up against the gravitational field again, so you lose kinetic energy, and you finally reach point B, let us assume, with speed vb, tangentially. No friction, mechanical energy is conserved. Gravitational potential energy plus kinetic energy here is gravitational potential energy plus kinetic energy here is gravitational potential energy plus kinetic energy here. All right, we have already agreed that we have arbitrarily chosen to be the gravitational potential energy 0 here, so that makes life a little easy. Let's call the mass of your roller coaster capital M, and you with a modest mass little m. So there we go. First, point A. No kinetic energy, only gravitational potential energy. So we have m plus little m times g plus h. That is the gravitational potential energy relative to this level. Then we arrive at C, where there is no gravitational potential energy, because I've set this 0, so we only have kinetic energy, which is 1/2 m plus little m times v at location C squared. And now we arrive at point B. So we have again picked up gravitational potential energy over this height. So we have this equals m plus little m times g times that height, which is 2r, plus the kinetic energy that we have at point B, 1/2 m v at location B squared. This is a very important equation. This is the conservation of mechanical energy. And notice that all these m plus m's cancel. And what you see immediately, that if you make h higher, that Vc is higher. That's immediately intuitive. If you start at a higher altitude, then obviously when you reach the ground level, you would have a higher speed. Well, you see that in front of you. Again, no friction. And also you notice that Vb will be higher if h is higher. So all of that is intuitively extremely pleasing. Now this picture is a little bit more complicated than you may think from this equation. Because what makes you think that you ever make it to point B. When you reach point B, by the way, you will be hanging inside this loop upside down. It's a very awkward feeling, I would imagine. But apart from that, what makes you think that you will actually reach that point B? So let's first evaluate that in some more detail. Let this be that circle. So this is point C, and this is point B. And you have here this velocity v of B. Now, what is required for this object to stay in orbit, to make this curvature with this speed vb, this tangential velocity vb, what is required that there is a centripetal acceleration which is downwards. And that centripetal acceleration equals vb squared divided by r. And let us now assume that this is exactly equal to g, so that gravity provides precisely the necessary centripetal acceleration to the center of this point. The roller coaster and you will now be floating when you reach this point B. You will experience no weight. I will get back to that. Just the same as we discussed in an earlier help session, that these astronauts in orbit, they have a tangential speed in orbit, let's call it v. There is a centripetal acceleration pointed towards the Earth, which is v squared divided by r. And that is exactly equal to their local g. And therefore, if you can recall what my arguments were, therefore, they are weightless. For the same reason, if this were the case here, then the roller coaster would be weightless and you would be weightless. Well, the way you could test that, and that's the example that I mentioned earlier with the astronaut, put a bathroom scale between your bum, so to speak, and the seat. You will see, if this is the case, that the bathroom scale will read 0. Even though you're hanging upside down, you're not falling at all, but you have no weight. All right. Let's now, by the way, first I want you to demonstrate that if you want this situation to occur, I want you to show that that will happen, and only then when the height from which you release it is 2.5 times r. In which case you reach at that point B a velocity, a speed, which I call the critical velocity. And so this is the critical height. If for some reason the h from which you start your roller coaster is less than 2.5 r, you never make it to point B. But what happened then? The following: you come down the slope, yeah, boing, you go inside here, and you fall out, and you crash. So this will give you a situation where you do not reach point B. So what now is necessary for you to reach that point B, apart from this special case that v squared over r is exactly g? If you want to play it a little bit more comfortable, then it's clear that v squared b over r should be larger than g, and therefore h should be larger than 2.5 r, and therefore the speed, the tangential speed that you reach at point B, will be larger than that critical speed which I just calculated. If that happens, the track will push down on the roller coaster. If this is the track, and here are the wheels of the track, everything is now upside down, and you are sitting here. The track will now push down on the roller coaster. the velocity, the speed, the tangential speed, is now Vb, which is larger than the critical value. Let us only draw the forces on you. You have a mass little m, so that is mg. But now there has to be a push from your seat onto you in this direction, which I will call n. And the reason why this has to be there is that we now have mvb squared divided by r must now be n plus mg. And remember, when this wasn't there, then we had the critical velocity at b. But we know this value is larger than the critical velocity. So there must be an extra force helping gravity to be sure that you have the necessary centripetal acceleration in downwards direction. So what do you experience? You're hanging upside down and you feel a push from your seat in down direction. Well, I'm sitting straight up now, you better believe me. And so I feel a push from the seat up. So what do I think? That gravity is down. Now imagine that you are here. You feel a push from the seat down. So you effectively think that gravity is up. So you perceive gravity is in this direction. So already you notice that there's no worry for you to fall. You don't even have any fear because you really feel gravity being up. This is a crucial equation. And this now, according to my earlier definition of weight, is really your weight. Now, if you want to call it perceived weight, be my guest. But if you wanted to, if you put a bathroom scale between you and your seat, that n in newtons, or if you calibrate it in kilograms or pounds, that's fine, that would indicate your weight. The bathroom scale would indicate n and nothing else. And in the case that I mentioned earlier, that the v squared divided by r is exactly g, that bathroom scale would indicate 0. So if you read the bathroom scale, you would really read this number. And I therefore call that your weight. That's my definition of weight. Now you're being given that, oh, not mg, you're being given that you read on the bathroom scale a weight mg, 1/2 mg. That's a given. And so I can rewrite this equation. So I get m vb squared divided by r now equals 3/2 mg. That's a given. M cancels. And so if you know what r is, and you know what g is, and I assume you do, out pops that velocity Vb, and that Vb better be larger than the critical value, otherwise you would have made a mistake. And if you substitute this Vb in our equation number 1, which I may have saved somewhere, where is my equation number 1? Here it is. If you substitute Vb in here, you can solve for h. And you better find that h is larger than 2.5 r. If not, you would have made a mistake. So that Vb substituted in equation 1 must give you an h which is larger than 2.5 r.